You are welcome to Dave Tut Academy, where we're devoted to building academic excellence in students for the STEM subjects. This particular video is going to be focusing on the physics exam prep as we go through the detailed solution to all the questions from Obafemi Awolowo University 2018 Physics Post-UTME Exam. Now, before we go ahead, we are soliciting that you go ahead and subscribe to the channel, click on the notification icon so that you can have access to all of our video resources as you upload them. Now, going through them, you can actually have a lot of resources that can help you prepare for your exam. Don't forget to like them. Don't forget to share with your friends and with your loved ones. And with that, let's head over to our video for today. So here in this question, we are asked that what is the peak voltage across a 10 Henry inductor in series with a 500 ohm resistance, assuming that a voltage of 20 volts, that's the root mean square voltage, and frequency of 50 hertz is applied across the circuit. Now, instead of just dabbling into this question and solving it directly, I would like us to consider the series RLC circuit, which consists of a resistor, an inductor, and a capacitor in series, and they also have a voltage with a particular frequency applied across the circuit. Now, if we want to label this, we have our resistance, then we have our inductor, we have our capacitor. Now, the inductive reactance is given as 2 pi level, while the capacitive reactance is 1 over 2 pi Fc. All right. Now, for this particular circuit, we can consider that a voltage V and frequency F is applied across the circuit. That would normally generate a current which will be the same because current in series remains the same, okay? But now with the current that's flowing, the resistive load will take a voltage drop VR, okay? The inductor will take a voltage drop VL, all right? And then the capacitor will also take a voltage drop VC. So now we need to go ahead to analyze this so that we can know how best to handle questions like this. Now, as a rule of thumb, if you are to consider the voltage across the inductor and the capacitor and the current, it is noted that the voltage across the inductor leads the current by an angle of 90 degrees. So if this is the voltage across the inductor VL, but the voltage across the capacitor lags the current by 90 degrees. So we can have VL and VC as shown and the current. And if we are to resolve this, now we can have it that if we resolve the voltages VL and VC, that will give us here VL minus VC, okay? And then the voltage across the resistor will be in phase with the current, so we have VR here. We can see that this is giving us a Pythagorean triangle already. So if we want to find the resolution of these voltages, it's just for us to complete our diagram, just as if we are working with parallelogram law of vectors. So the resultant voltage, which is the voltage applied across the circuit, V, can be gotten by the Pythagorean triangle. And we know that by that, we are going to have the value of V to be, that will give us V raised to power 2. We are going to have V raised to power 2 is equal to VR raised to power 2 plus VL minus VC all raised to power 2. Okay, that's just like the Pythagoras theorem. So if we are to solve this, the voltage applied across the circuit will be the square root of VR raised to power 2 plus VL minus VC all raised to power 2. So now, we know that the VR is IR, the current multiplied by the resistance. And so VR raised to power 2 will be I raised to power 2 multiplied by R raised to power 2, right? Now, in the same way, the voltage across the inductor, VL will be the current multiplied by the inductive reactance, SL, And so V all raised to power 2 will also be I raised to power 2 multiplied by XL raised to power 2. And for the capacitor, it will also be V raised to power 2 for capacitor is current of the capacitor multiplied by the capacitive reactance VSC raised to power 2. So if you are to substitute all this into our equation, we can see that our V now, but instead of just using V, you can also say V is IZ, where Z is the impedance of the circuit, okay? IZ is going to be the square root of, now, instead of writing VR, we have I raised to power 2 multiplied by R raised to power 2 plus VL and VC. They both have I raised to power 2 common, so we can have XL minus XC. That's the difference in the inductive reactance and the capacitive reactance. So this I raised to power 2 can be factored out of the square root to cut the other I, so that our Z is the square root of R raised to power 2 plus the inductive reactance minus the capacitive reactance all raised to power 2. Now, this formula is what is regarded as our impedance. That's the impedance for the circuit. And using these parameters, we can go ahead to do our calculations. Now, for this particular question, we are noting that we are not talking about the capacitor at all. So that means we can knock out the capacitor and the capacitive reactance so that we're only left with R and L. So that's what we're going to do now. We're going to head over to the question and solve in that manner. But if you have the RLC now, we know how to go about it. So if we are to draw our RL circuit, we have our resistor, we have our inductor, we have the voltage applied across it, and we have the circuit. So here we have our resistance to be 500 ohm and the inductor to be 10 Henry. We have 20 volts and 50 hertz applied across the circuit. Now we know that the current I will flow through, but we need to know that the voltage that we're given is the root mean square voltage. But we're asked to find the peak voltage. So our answer will need to reflect that. We're asked to find the peak voltage, but we are given the root mean square voltage. And that's the peak voltage across the 10 Henry inductor. So we can now go ahead to say we want to try and solve this. Now the inductive reactance is going to be 2 pi FL. And we have been given F and we've also been given L. Then we have our current I flowing through the circuit. So now, let's go ahead and try and solve this particular question. In trying to solve this particular question, we are going to see that first, let's calculate the inductive reactance, XL. SL is 2 pi FL, and that will be 2 multiplied by pi multiplied by frequency, which is 50 hertz, multiplied by the inductance, which is 10 Henry. If you calculate that, that will be 1,000 pi ohms. So that's the value of the inductive reactance. Now, the impedance from the formula that we know we need to use, that will be the square root of R raised to power 2 plus the square of the inductive reactance. So if you have to put in these values, R is 500, so we have 500 raised to power 2 plus the inductive reactance have been calculated to be 1,000 pi, so we have 1,000 pi raised to power 2. So if you bring in our calculator, that will be 500 raised to power 2 plus 1,000 pi raised to power 2. So if you find the square root of that, that will give us 3,181.13 ohms. So the impedance for the circuit is 3,181.13 ohms. So since we now know the voltage and we know the impedance, we can go ahead to find the value of the current, recalling that the voltage is current multiplied by impedance. So the current I, we can evaluate to be voltage over Z, and that will be 20 volts divided by 3,181.13 ohms. So our current will be, let's take our calculator and say 20 divided by the previous answer. That's 6.287 exponent minus 3 amps. That's 6.287 milliamps. All right, because milli is 10 raised to power minus 3. So now this is the current across the whole circuit, and it's going to be the same remains the same because current in a series circuit remains the same. So now we can now find the voltage drop across the inductor. Since we now know the current and we know the inductive reactance of the inductor, we can now know that the voltage across the inductor is going to be current multiplied by the inductive reactance XL. And since we know the two values, that will be 6.287 exponent minus 3 multiplied by 1000 pi. That's the value of the inductive reactance. Okay, so if we bring in our calculator, just our former answer multiplied by 1000 pi. That's 19.7514 volts. 19.7514 volts. But we need to recollect that this is because we are using the root mean square voltage across the circuit, so this is the root mean square voltage across the inductor. This is VL root RMS. But we are asked to find the peak voltage. So the formula relating the peak voltage to the root mean square voltage is peak voltage is equal to root 2 multiplied by VRMS. So in this case, we have root 2 multiplied by 19.7514 volts. So if you have to evaluate that times root 2, is 27.9327 volts. That's 27.9327 volts. And that is the peak voltage across the 10 Henry inductor. And so our correct answer is option B. In this question, we're asked to find the velocity ratio of an inclined plane inclined at an angle of 30 degrees to the vertical. Now, the question looks very, very simple, but if one is not careful, one is going to miss it. Why? In the question, we are told that the inclined plane is inclined at an angle of 30 degrees to the vertical. They were explicit to tell us is to the vertical. So if you are to show our diagram, what we are going to have is something like this. Let's say this is a wall, and we also have the floor. Okay? And then the inclined plane is inclined at an angle of 30 degrees to the vertical. The vertical is the upright standing one. 30 degrees to the vertical can then be shown as this. This is 30 degrees. Okay? We already know that this is forming a right angle at the base. But what is the formula for the velocity ratio? The formula for the velocity ratio is given as 1 over sine theta. But now, what is theta? Theta is the angle inclined to the horizontal, not the angle inclined to the vertical. Theta is the angle inclined to the horizontal. So we need to find what is the angle inclined to the horizontal. In the diagram, we are given that 30 degrees to the vertical. If you use that, we are going to miss this question. So to the horizontal, this angle being shown in blue is our theta. And looking at the diagram, we can see that the sum of the angles of a triangle, 90 degree here, plus the 30 plus angle theta, they are going to be 180. So that theta will be 180 minus 30 plus 90. So we are doing this because the sum of angles in a triangle is 180. And already we see that from the diagram, we're having a triangle. So our theta will be 180 minus 120, and that is 60 degrees. So now we can go ahead to plug in the right value into the formula for the velocity ratio. So we can say that the velocity ratio is 1 over sine 60, not sine 30. So, and that will be 1 divided by, what is sine 60? Sine 60 is root 3 divided by 2. So if you are to swap, that will be 1 multiplied by 2 over root 3. And that's 2 root 3. But that's not included in our options for the answer. So what we just need to do is to we can say we want to rationalize or multiply the surd at the denominator, and we'll multiply it to the numerator and denominator as being shown. And this will give us 2 root 3. Then root 3 multiplied by root 3 will be option root 3 raised to power 2. The power and the roots, they will cut out. So we have 2 root 3 over 3. And that is the solution. Option D is the correct answer for the question. That's option D. What is responsible for the conduction of electricity in semiconductors? We are given these options: free mobile electrons, and holes only, free holes only, free mobile electrons, and ions. Now, as a rule of thumb, we know that electrons, they are the conductors of electricity in conductors, okay, metallic conductors, and then in semiconductors. Electrons are going to be the medium of transmission of electricity. But when it comes to holes, holes are only used by semiconductors, okay? And then when we're talking about ions, ions are only used by electrolytes or what is called the ionic compounds. Now, these are solutions that are able to conduct electricity. So, looking at our options, the correct option will be option B. That's free mobile electrons and holes only. That's what conducts electricity in semiconductors. In this question, we are told that a car moving with a velocity of 72 km per hour was brought to rest in 10 seconds by a constant retarding force. Okay, so we are asked to calculate the total distance that is covered during this 10 seconds time. So if you have our car as shown in the diagram, we are told that it's moving with a velocity u, initial velocity u is 72 km per hour, and then is now undergoing a constant retarding force in 10 seconds such that after traversing a particular distance, you can call that distance s, okay? This distance s. So to differentiate from our 10 seconds is the time. Then finally it came to rest, meaning that the final velocity at rest, the final velocity v is 0 meter per second. We are asked the total distance covered during this time. Now we are given the velocity in kilometer per hour, and we are given the final velocity, as we note, in meter per second. That means before we go ahead, first and foremost, we need to convert 72 kilometers per hour to the appropriate value in meters per second. The SI unit for velocity is meters per second. So how do we go about to do that? I'm going to be showing the step that I personally like. I'm going to say 72 kilometers per hour. That's divided by 1 hour. Now I'm going to be juxtaposing with the units. For example, 1 hour is actually 60 minutes. So if I said 1 hour over 60 minutes, is the same as if I'm saying 1 hour over 1 hour, and that's going to cut out. So I'm actually being consistent with this. Then I can say that 1 minute is actually 60 seconds. So I can say 1 minute divided by 60 seconds. I'm still dividing by the same value, and that will be 1. But if you notice, my units are going to now be converted to seconds. Hours will cut out, then I will have 60 seconds. Then for the kilometer, I know that, okay, 1 kilometer will need to be at the denominator to cut the kilometer up. But 1 kilometer is also 1,000 meters. So the kilometers will cut out, and I have meters per second. That is a wonderful way I've been doing my conversion, and they are always foolproof. So if you are to cut out with all this, here 0 can cancel these 2 zeros. So 6 and 6 is 36. 36 from 72 is 2. So this is 20 meters per second. So 72 kilometers per hour is 20 meters per second. If you know this beforehand, you can just plug it in. But if you don't, this is the way to go about it. So we now have our initial velocity as 20 meters per second, final velocity as 0 meters per second, and then we are looking for the distance covered given the time t is 10 seconds. If you draw a velocity time graph, there are 2 ways to go about this. First, if we draw a velocity time graph, so we can have this. This is our u, which is 20 meters per second, and then the time t is 10 seconds. So there is a constant retardation, and that will be as shown below. Now, the distance for the distance covered by the car will be the shaded area under the graph as shown, And if you look at the graph, that is a triangle. So the distance is the area under the graph. If we have a velocity time graph and we want to find the distance, that is given as the area under the graph. And this is a triangle, so the area is half base multiplied by height. And that will be 1 over 2 multiplied by 20 multiplied by 10. And 2 can cut 20 to be 10. So we have the distance to be 100 meters. Now, alternatively, we can also use the formula method using the equations of motion to solve this particular question. Okay, so we are going to be asking our question, what equations are actually useful for us if we want to go about when we have the initial velocity, we know the final velocity is 0, we are given the time. Well, we can use v is equal to u plus at to find the value of the acceleration. Now, v, the final velocity is 0, the initial velocity is 20. We don't know acceleration, but we know time to be 10. And solving this, our acceleration will be minus 20 meters over 10, which is minus 2 meters per second square. Okay? That's meter per second square. Not meter per second. It's 2 meters per second square. So now, since we know our acceleration to be minus 2 meters per second square, we can now use the formula for the distance. S is equal to ut plus half at square. And that will be 20 multiplied by the time t, which is 10, plus half. The acceleration is minus 2. It's minus because it's a retarding force. So we use the negative sign. So that will be 200 minus, this is 1. Okay, 10 raised to power 2 is 100. And that will be 100 meters. So using any of this method, whichever one is suitable for you, you can get the distance to be 100 meters. And that's option C. All right, that's all about this question. Here, we are told that a 300 gram body moving with a speed of 6 meters per second collides head-on with a 900 gram body, which was initially at rest. The collision was elastic, and we have to find the final velocity of the 300 gram mass. Well, right from the onset, I'm going to convert the bodies into kilograms. So I'm going to have 0.3 kilogram and 0.9 kilogram. Initial velocity for the body 1 is 6 meters per second. That's U1. The initial velocity for the second body, we are told that it was at rest. So the initial velocity U2 for the second body is 0 meters per second. That's before collision. Now we are going to assume a velocity V1 for the first body after collision. And we are going to assume a velocity V2 for the second body after collision. Okay? Now, both of them are assumed to be in the positive direction, moving in the positive direction. So we're told that the collision was elastic. Now, what does that imply? If the collision was said to be elastic, there are two key features we need to note since they were told that it is elastic. And the first is that we are going to have conservation of momentum. Now, momentum is defined as the product of the mass and the velocity. So momentum before and momentum after are going to be equal. And then we are also going to have conservation of kinetic energy. And kinetic energy is half multiplied by the mass multiplied by the square of the velocity. So meaning that for these two bodies, the momentum and the kinetic energy are going to be the same before and after collision. If you use this principle, we are going to get our equations that will help us to solve for the final velocities of the two collision bodies after collision. So first, if you are to pick the conservation of momentum, so we want to consider the conservation of momentum for the bodies. Now, before collision, we are going to have m1 multiplied by u1 plus m2 multiplied by u2. After collision, we are going to have m1 multiplied by v1 and m2 multiplied by v2, where u is initial and v is the final. 1 for the first body, 2 for the second body. So if you are to put our value, we are going to have 0.3 multiplied by 6, okay, plus 0.9 multiplied by 0, because initially the second body was at rest. So that's 0 meters per second. Then that's equal to, after collision, we are still going to have the same mass, 0.3 V1 for the first body and 0.9 V2. 0.9 V2 second body. So now if you are to just multiply out and simplify this, we are going to have 0.3 multiplied by 6. That will be 1.8. Okay. Now, the other value is 0. So we have 1.8 is equal to 0.3 V1 plus 0.9 V2. And if you are to just rearrange that, we have 0.3 V1 plus 0.9 V2 is equal to 1.8. Now we can divide by 0.3 all through because it's common to the three of them. It's a factor of each entity. So we are going to have V1, then 0.3 in 0.9, that will be 3, plus 3V2 is equal to 0.3 in 1.8, that will be 6. All right? So we can have this as equation 1, looking at the conservation of momentum. Now, moving forward, looking at the conservation of kinetic energy half mv squared. Now we can look at, before collision, we are going to have half m1 u1 raised to power 2, okay, plus for the second body half m2 u2 raised to power 2. Now the same is going to be the value after collision. So we have half m1 v1 raised to power 2, okay, plus for the second body half m2 v2 raised to power 2. Okay, good. So now we can go ahead to say we also want to simplify this. We can say, instead of writing half is common to all the entities, so we can just cut them out. All the halves, they can divide themselves out, okay? U, the initial velocity for the second body is 0. So that will leave us with the mass of the first body, 0.3 multiplied by the initial velocity raised to power 2, which is 6, is equal to the mass of the first body, 0.3 multiplied by the final velocity of the first body, that's v1 raised to power 2, then plus the mass of the second body, 0.9 multiplied by the velocity of the second body raised to power 2. So we have this question here. If we said 6 raised to power 2 is 36, so we have this as 0.3 multiplied by 36 is equal to 0.3 v1 raised to power 2 plus 0.9 v2 raised to power 2. So again, we can see that 0.3 is also common. This will simplify the work for us. So if you cut out as appropriate, we are going to have v1 raised to power 2 plus 3 v2 raised to power 2 is equal to 36. So this we can call equation 2. So we have two equations in two unknowns, and that means that we can go ahead to solve for these two unknowns using these two equations. If you are to write them out, the first equation, we have v1 plus 3v2 is equal to 6. That's equation 1. Then in the second equation, we have v1 raised to power 2 plus 3v2 raised to power 2 is equal to 36. That's equation 2. We want to go ahead to solve this. If you consider equation 1 and we make v1 the subject of the formula, we can say from equation 1, v1 is equal to 6 minus 3v2. So we are to use this in equation 2. So using v1 is equal to 6 minus 3v2 in equation 2, bracket, what we are going to have is, instead of v1 raised to power 2, we are now going to have 6 minus 3v2 all raised to power 2, since that's the value of v1, plus 3v2 raised to power 2 is equal to 36. So if you are to expand the bracket, we can say it's 6 minus 3v2 multiplied by each other plus 3v2 raised to power 2 is 36. So we have 6. First, we have 6 multiplied by 6, and that is 36. Okay, minus 6 multiplied by minus 3v2, that will be minus 18v2. Okay, then minus 3v2 multiplied by 6, again, that will be minus 18v2. Then minus 3v2 multiplied by minus 3v2. The negative signs will multiply each other to be positive. 3 times 3 is 9v2, then v2 raised to power 2 plus 3 V2 raised to power 2 is equal to 36. So now we can further just simplify this. We can say this is now, for us, we have 36 minus 18 minus 18, that will be minus 36 V2. 9 plus 3 is 12 V2 raised to power 2 is equal to 36. Now, when 36 moves to the other side, it will be subtracted, and that will just take out the 36, so that we have 12 V2 raised to power 2 is equal to 36 V2. Dividing both sides by 12 V2, on the left-hand side, we are going to have only V2, and on the right-hand side, we are going to have 36 divided by 12, which is 3. So that's 3. So our V2 is equal to 3 meters per second. Now, that is the velocity of the second body. We are asked the final velocity of the 300 gram mass. So this is the velocity for the 900 gram mass. But we are looking for the velocity for the 300 gram mass, and that is V1. Okay? So we need to substitute for the value of V2, because we know that initially we said V1 is 6 minus 3 V2. So our V1 in that case, if you substitute for the value of V2, so we have V1 is 6 minus 3 multiplied by 3 meters per second. And that will be 6 minus 9. And that's minus 3 meters per second. So the velocity of the 300 gram body, which is 0.3 kilogram, is minus 3 meters per second. It's minus 3 because that means it's going to bounce back. And after hitting the bigger body, it's going to bounce back. So it will move backward from the direction it's coming before. So the velocity is negative. And our correct answer is option A. So here in this question, we are given a 5 kilogram uniform plank, which is balanced horizontally on a support by 2 weights attached to its ends. The plank is 2 meters long, and the support is placed at 0.5 meters from one end. If the mass near the support is 10 kilograms, what must be placed at the other end? So let's interpret our question appropriately. So this is the 5 kilogram uniform plank, okay? And then we are told that it is uniform. So the weight will act exactly down the middle. So we are going to have this as the weight of the uniform plank. That's 5 kilograms, all right? Then we are now told that it is 2 meters long. So, and a support is placed at 0.5 meters to its end. Now we have a support. We have a weight acting on both ends. If you have this as weight 1, and at the other end, we have this as weight 2. Okay? Then we are asked that, we are told that 0.5 meters from one end, we have a support. So if we bring this as a support, remember that the plank is 2 meters long. So now we have this support at 0.5 meters from one end. So now we can indicate, we've indicated that support already. Then we can put in the distance that between this support and this end, as we are told in the question, that is 0.5 meters. So this is 0.5 meters. Now, the plank, know that the plank is 2 meters long, and the weight is acting exactly at the middle. So the midpoint of the plank is 1 meters. So this is 1 meters. And then the other end is also 1 meters, but we've taken 0.5 meters out. So this will remain 0.5 meters. Okay? That's the appropriate interpretation of the information that we are given from the question. So now, we're told that the mass near the support is 10 kg. So this is the mass near the support in this diagram. That's W1. So W1 is 10 kg. Now we are now asked that what's the mass that must be placed at the other end? We are looking for W2. This is the appropriate way to interpret this question. Now, how do we go about trying to solve this particular question? Now, what we need to note is that we are told that it is balanced horizontally. That means it is in equilibrium. It's not tilting to any side. It is standing balance. And in that particular situation, what we need to note is that the sum of the clockwise moments and the sum of the counterclockwise moments are equal. So now, if we are to take the clockwise moment and we are to take the counterclockwise moment, the two are going to be equal to each other, and we can take this moment about the support. So the 5 kilogram weight will go clockwise, and the weight 2 that we are looking for will also go clockwise, while the 10 kilogram weight will go counterclockwise as shown in the diagram. So if you are to use this and plug in into the formula for the moment, that means that we should be able to find the value of the second weight that was given to us. So what is the formula for the moment? The moment is given as force multiplied by the perpendicular distance to the force. So it is force multiplied by perpendicular distance. So now if you notice in this diagram, we are only giving kilograms and we are only giving the mass, and force is mass times the acceleration, in this case, acceleration due to gravity, g. But g will be common to all, so we don't need to be plugging the value of g because they will still cut out. So we can just say we can use our mass multiplied by the distance for this particular questions, all right? So that's what I'm going to be doing. So we want to take the clockwise moment will be 5 multiplied by the distance, that's 0.5 meters, okay, plus the weight, W2 that we're looking for, and its distance will now be 1 plus 0.5, and that will be 1.5 meters. So this is going to be equal to the counterclockwise moment, which is 10 kg multiplied by the distance to the support, 0.5 meters. So this is what we need to evaluate. 5 multiplied by 0.5 is 2.5. So no, that will be 2.5 plus W2 multiplied by 1.5 is 1.5 W2. 10 multiplied by 0.5 is 5. Okay? So that 1.5 W2 is equal to 5 minus 2.5 when 2.5 move to the right-hand side. And that is 2.5. And we have our weight 2. Our weight 2 will be 2.5 divided by 1.5. So if we are to find that, we have 2.5 divided by 1.5. That's 5 over 3 or 1.67 kilogram. That's the value of the second weight that must be placed at the other end. But interestingly, from the option, that answer was not included in the option. And perhaps the exam body, they want to check maybe you are just picking any answer. But for this particular question, the correct option is not in the given options. In this question, we are told that a 50-gram ice at minus 10 degrees Celsius gradually turns to water at 25 degrees Celsius. And we are to find the amount of heat consumed in the process. We are given the specific heat capacity of ice, the latent heat of fusion of ice, and the specific heat capacity of water. Now, we need to know the processes that ice will go through to turn into water. Now, in this particular question, there are going to be 3 stages. First, the ice being reduced down to water. Then, at the point of which it is becoming water, then the increase in temperature of water from 0 degrees Celsius to 25 degrees Celsius. So, we are going to take those 3 steps. But now, we are giving 50-gram ice, and we need to convert to kilogram. Now, to do that, that will be 50 multiplied by 1 divided by 1,000. The grammage will cut out so that 0 will also cut out. Now, we have this is 5 over gram 100 kilogram. So this is 5 over 100, and that will be 0.05 kg. That's the grammage of ice that we are talking about. Now, if we are looking at this as the 3 stages that the process will undergo, we have the stage at which the ice is at minus 10 degrees Celsius, then the 0 degrees Celsius where we're having transition from ice to water, and then the water being heated up to 25 degrees Celsius. It will transition through each of these stages. So in the first instance, we can say we want to indicate our ice. Okay, so let's say we have this as the 50-gram ice, which we have already gotten to be 0.05 kilogram. So let's have it in our container that we're going to be heating up, okay? Then, now, that will take, if we heat from minus 10 degrees Celsius, it will take the ice down to 0 degrees Celsius. And at 0 degrees Celsius, there's going to be a transition of the ice to water. So the ice will be undergoing a process in which it will be turning into water. As shown in the diagram, we have a mixture of ice and water. Then after that is accomplished, the water will also be heated up to 25 degrees Celsius. So these are the 3 stages that we need to note. We need to know the heat consumed per stage. And if you add them together, we know that that's the heat consumed by the whole process, okay? So now, if you apply heat for each of the stage, you can call that H1, H2, and H3, okay? Let me add more of these signals, okay? So we have H1, H2, and H3. So we have H1 to be the mass of the ice multiplied by the specific heat capacity of the ice multiplied by the change in temperature for the ice. Ice going from minus 10 degrees Celsius to 0 degrees Celsius. It is change in the value, okay? So the mass was given as 0.05 kilogram. The specific capacity of ice was given as 2,100 joules per Kelvin per kilogram, okay? Now, the change in temperature will be 0 minus minus 10. Please, you don't want to make that mistake. It's not minus 10. It is 0 minus minus 10. We are going from minus 10 to 0. Now, ideally, the temperature is supposed to be in Kelvin, all right? But because both the Celsius and the Kelvin, when we're actually transitioning between them, the changes are linear. If you have a 10 degrees Celsius change in Kelvin, it's also going to be a 10 Kelvin change in temperature, okay? So since it is changes, we don't need to be converting to Kelvin. I will just take the change in the temperature. So like this now, I'm going to have this to be, if I want to calculate that, that will be 0.05 times 2,100 minus minus 10 will become plus. So I say times 10. So the first amount of heat that will be consumed in the stage in which the ice is being taken from minus 10 degrees Celsius to 0 degrees Celsius is 1,050 joules. That's the amount of heat that is consumed. Now, in this second case, in which the ice is transitioning into water, I'm going to have that. Now, the same mass will be in place, but instead of using the specific capacity, I'm going to use the latent heat of fusion, because that's what is taking place at this particular stage. So I'm going to have the mass multiplied by the latent heat of fusion. Then the temperature change here is not in constant because it's at constant temperature, okay? The ice is transitioning to water at constant temperature. So we have 0.05 multiplied by 3.34 times 10 raised to power 5 joules per Kelvin. So if you are to multiply that at 0.05 times 3.34 times exponent 5, that's 16,700 joules. Okay? Ice. All right, that's 16,700 joules. And then after we have gotten the ice transformed into water, now the water will start from 0 degrees Celsius to 25 degrees Celsius. And so for us to calculate the heat consumed, we also use MC multiplied by change in theta. Now change in theta is 25 minus 0 now, okay? So the mass of water is also going to be the mass of the ice because it's still the same substance we are talking about. It's just a transition in state. So we have 0.05 times 4,200 times the change in temperature now is 25 minus 0. So that will be 25. So if you bring in our calculator, 0.05 times 4,200 times 25, that's 5,250 joules but we're asked to get the amount of heat that is consumed in the process. So this whole process is going to take a total of the summation of the heat that is consumed per process. So the amount of heat consumed in this process of turning 50-gram ice at minus 10 degrees Celsius to water at 25 degrees Celsius will be the sum of the heat consumed per process, and that will be 1050 plus 16,700 plus 5,250. And we have to evaluate that, plus 16700 plus 5250, that's 23,000 joules. And 23,000 joules is the same as 23 kilojoules, 1,000 kilojoules. Okay, so the correct option is option C. Good. 50, that's the solution to our problem. In this question, we are told that a car travels due west for 10 minutes at 50 km per hour and then in the direction 45 degrees west, and we are to find the average speed. But looking at the options, we can see we are giving our options in kilometers per hour. So we need to be careful so that we don't just dabble into the question, working in meters per minute, and then needing to translate back to kilometer per hour. Now, we are told that is traveling due west. So our cardinal point being shown here, this is north, south, east, and west. That means our car is starting and heading first and foremost due west for 10 minutes. So if you have this as the movement due west, so this is 50 kilometers per hour, and it does that for 10 minutes. Okay. And then it also moved in the direction 45 degrees west of north. So from that particular point, we now have 45 degrees west of north to be taking 25 kilometers per hour, and that was done in 5 minutes. So if we are to consider this, now the final displacement for the vehicle will be as shown in the colored ink, but that is the displacement. We are now being asked, what is the average speed of the car? Well, it's interesting to know that in this particular question, all the information, particularly regarding the direction, is actually not needed. We know that speed is a scalar quantity, and speed is given as distance over time. So from that formula, the distance is speed multiplied by time. So all we need to do in this particular question, we don't need to bother ourselves with the direction. It's just that we are to take the two case scenarios, the first journey at 50 km per hour and the second at 25 km per hour, find the distance and then evaluate total speed, the average speed of the car. So for the first case, when it's traveling at 50 km per hour for 10 minutes, the distance will be speed multiplied by time. Now the speed is 50 km per hour multiplied by the time. The time is 10 minutes. Okay. Now we have minutes and hour. We need to put them in the same units. This is where we are prone to make mistake. So 10 minutes, let's say divided by 1, but now we know that 60 minutes makes 1 hour. Okay. So the minutes from the denominator and numerator, they will cancel out. The hours will cancel out. Okay. So now we can have our distance to be 500 kilometers divided by 60. That is the distance. You can see how I took care of the unit so that hours and minutes are not constituting any nuisance for me. So in the second case, we're also going to do the same thing. Traveling at 25 kilometers per hour for 5 minutes, okay, we can find the value of the distance. So the distance is now 25 kilometers per hour over 1 hour multiplied by time. That's 5 minutes over 1. But we need to convert our time appropriately. And we are noticing that 60 minutes make 1 hour. So we can cut out the units appropriately. And this will leave us with 25 times 5 is 125 over 60 kilometers. So now, that means that since we know the distance covered in the first case and the distance covered in the second case, the total distance will be 500 over 60 plus 1 was 25 over 60. And that would be 625 over 60 kilometers. That's the total distance that was traveled. Now, what is the total time that was used to travel? The total time will be the 10 minutes plus the 5 minutes. So you can just say that is 10 plus 5, and that is 15 minutes. So now, 15 minutes, our answer was given in hours. So we need to convert minute to hour, and that will be 15 multiplied by 1 over 60 minutes. So the minutes will cancel out. So we have this to be 1 over 4. Actually, 15 minutes is 1/4 of an hour. Okay. So we can now say that from here, we can find the average speed. The average speed of the car will be the total distance divided by the total time, as we have noted before. So that will be, the distance is 625 over 60 divided by the time, which is 1 over 4. So we have to just appropriately evaluate that. That will be 625 over 60 times 4 over 1. 4 can go here, 15. Okay. So we have 625 over 15 kilometers per hour. And if we bring in our calculator, 625 divided by 15, that will be 41.67 or 41.7 kilometers per hour. So the correct option for us is option D. That is the right answer. In this question, we are asked that in which of the following groups are the radiations arranged in decreasing order of their wavelength? I would like to bring in the diagram for the electromagnetic waves so that we can evaluate how do we get the decreasing order of the wavelength of these particular waves that we are given. So here, the diagram was sourced from the internet, and the appropriate citation was given below. You can check it out. You can also download it if you want to make use of it. Now, if you want to take note of this, let's note the radio wave, microwave, infrared. If you write them out, we have radio wave, microwave, infrared, visible, ultraviolet, X-ray, gamma ray. You can use any means to try and remember this. You can use an acronym for this. You can say real men in value upholds extra grace, or you can come up with your own so that you will remember this again and again. For me, real men in value upholds extra grace. I think I love that. So now we are talking about the decreasing order of their wavelengths. The question, we are talking about the decreasing order of their wavelengths. So if you look at the wavelengths, we can see that for radio waves, we have 10 raised to power 3. For microwave, we have 10 raised to power minus 2, and that is a decrease. Infrared, 10 raised to power minus 5, and it's just decreasing by and by, just like that. So you can say that the radio waves have the highest wavelength, gamma rays have the lowest wavelength, and we are asked in decreasing order of their wavelength. So that will be moving from left to right, okay? So in this direction, we have the academic is decreasing wavelength. The radio wave have the highest, gamma rays have the lowest. So in the direction of arrow shown, that is the decreasing wavelength. I don't mean that we are talking about frequency. You can see that is also the direction of increasing frequency, okay? The frequency for the radio waves are lowest, for the gamma rays are highest. So now, once we know this, we can now use that for this our question to actually evaluate correctly the appropriate order for the decreasing order of their wavelength. So now if we take it, that means that we have radio waves first, and with that, options C and D are going to be useless for us because they are not starting with radio waves, they are ending with radio waves. We don't have any microwave included. Let's knock off option C and D, okay? So there's microwave. We are not talking about infrared wave, not talking about visible rays, not talking about ultraviolet wave. The next one is X-rays, and option A is not putting that correctly. So the correct option for us is option B. That is the correct order in decreasing order of the wavelength for the electromagnetic waves. In this question, we are told that an object placed 10 centimeters in front of a convex lens of focal length 20 centimeters. Okay, focal length F is 20 centimeters, object is placed 10 centimeters. So U is 10 centimeters. So we are to find where the image is going to be formed. Now, from the question, we can get our U to be 10 centimeters and F to be 20 centimeters. Now, we are looking for the position of V. Normally, if you really understand the properties of convex lens, how images are formed, you can answer this question on the go. If I want to show this, I will say, let me have my convex lens. Okay. And then since I understand the properties of how to get my image from my object that is placed in front of a lens, I can say that, okay, I have the center of curvature. Principal axis is the straight line drawn. Center of curvature is the middle of the lens. And then I'm also reciprocating the principal axis on the other side of the lens. So if I have the focal length here, I'm going to have F1 at the other side. Now the object is placed 10 centimeters. Since F is 20, 10 will be in between F and the center of curvature. Now rays passing through the image, when it gets to the lens, it will go and pass through the focal point on the other side as shown. Okay. And then another ray will pass through the center of curvature. Center of curvature is the middle of the lens, just as shown also. Now, the two rays, will notice that they are divergent. They are just expanding away from one another. So, in that case, we need to reverse to the other direction from where they are coming. So, just as shown, I will reverse back. Okay? And then also reverse back from the center of curvature. And then the point of intersection will be the point where the image of that object will be shown. Okay, so, and now I can just show that from the diagram. So this is going to be the image. Okay, now from this, since I just use the rules of construction of my rays of light passing through an object, that's just as shown, and because they are divergent, I needed to reverse them. So now I can see that for an object that is placed between the focal point and the center of curvature, I'm going to have an image that is formed at the focal point, and that focal point, you can see, it was given as 20 centimeters. So the image is formed at the focal point. The focal point for this particular question was given as 20 centimeters. And then, of course, it is virtual, it is erect, it is magnified. So it is 20 centimeters, but now it is to the left of the lens. And with that, I can just pick my correct option to be option B. But if you don't really have a good grasp of this, the other way to go about it is to use the lens formula. And now, what is the lens formula saying? The lens formula is saying that 1 over F is equal to 1 over V plus 1 over U, where V is the image distance, U was the object distance that were given as 10 centimeters, F is a focal length that were given as 20 centimeters. So if you are to plug in this value, you can just say that means 1 over 20 is equal to 1 over V plus 1 over 10. U is 1 over 10. So if you move 1 over 10 to the other side, 1 over V will be 1 over 20 minus 1 over 10. Finding LCM, 20 in 21, 1 times 1, 1 minus 10 in 20 is 2, 2 times 1 is 2. So I have 1 over V to be minus 1 over 20, meaning that V is minus 20. You can see we are also getting the same thing. It's now minus 20 centimeters, minus because it is to the left side of the lens. It's being reflected back. It is virtual. So the correct option is option B. So that's all we are going to be having in our lecture today. We hope that this will be of benefit, of use to somebody out there. Don't forget to subscribe to our channel. We have a lot of resources that you can use to enhance your academic excellence. And that's our desire, that you go out and be the best, that you gain that admission, that you excel in your studies. And as you do all this, we know that all will work out together for good. Until next time, God bless you.